Welcome to today's video. Today we're going to talk about Riemannian manifolds, or maybe more concretely, pseudo-Riemannian manifolds, which is the, the spin above Riemannian manifolds that we actually need to talk about space-time. Anyway, first of all, let me define a metric tensor. This should be familiar already because we've been through it twice, once in the second video and once in special relativity, but let's do it anyways. A metric tensor G in a differentiable manifold is a twice covariant type 02, twice covariant, symmetric tensor field. So important, it has to be symmetric and twice covariant. We will discuss why it has to be symmetric, because of course there's a reason you want it symmetric to define a metric tensor. Now, its components on an arbitrary basis are given, of course, acting with the metric tensor on the elements of the basis, as usual. And in a coordinate basis, the metric tensor, you can write, of course, as that, the components, of course, contracted with elements of the basis, which in a coordinate basis, of course, are the differentials. It is really important not to confuse the metric tensor with what we define as the line element. The line element is something that you remember from special relativity. We did define it in special relativity already. Now, the metric tensor is a tensor. So you see, in a coordinate basis, you write as the components, right, of the metric tensor times the elements of the basis. The differentials of the coordinates are elements of the coordinate basis. Oftentimes in physics, this is called a metric. The line element, when you have a line element, oh, that's the metric. Not quite, no. I mean, even though it's abused like that, the line element is not the metric. The metric is the tensor, and the line element is not. We will see this much better at the end of the video, but for now, let me just tell you like how this relates to a length in a way. So this differential, I can write, of course, if I parameterize, imagine that I'm talking of a curve in a manifold, right? So in that curve, I can parameterize the curve as this one as, let me write like that, dx mu dt, let's say that t is the parameter of the curve, dx nu dt, right, and then dt outside. And this thing can be understood as the norm of a velocity vector, so in a way, this ds is related with something like the norm of some tangent vector. Remember, this is x dot mu, the coordinate expression of the tangent vector to the curve, and this can be understood as something like the square root of the norm square of the tangent vector, and therefore this is what you integrate to get the length of a curve, right? Velocity times time integrated from the initial time to the final time. So this we will see in much more detail at the very end of this video, because there are some notions that we have to introduce. But I think at this level, it is important to distinguish what it is the metric tensor from the line element, which happens to be a differential restricted to a trajectory, a curve. That's why we call it line element. All right? Because when we integrate the line element, we get the length of the curve. Again, more on this at the end of the video, but hopefully we clarified the very big difference between the metric tensor and the line element, even though they look kind of similar, and we will call it the metric in physics often to both of them. Now we have a metric tensor, therefore we can define a metric. And a metric means we can define a notion of norm, a notion of distance, and a notion of angles, and even an inner product. Well, now that we have a metric tensor that will help us define a metric, now we can define the norm of a vector. So how do I define the norm of a vector? Well, let me define it like this. The norm of a vector is the action of the metric on two copies of the vector. So it would be in an arbitrary basis, GAB, VA, VB. Right, so that's the norm of the vector. And if we have a norm, we have a notion of distance. Remember that displacement vector that we can have, something like when you have deltas in here, right? And that notion of distance is why we call it like metric. We can actually measure, now we have distances. Now, now why you see that why it is important that the metric is symmetric. The metric is symmetric because when I use it to define distance, I want the distance between you and me to be the same as the distance between me and you. So you get that if the tensor is symmetric. Now, typically in Riemannian manifolds, you also demand that the metric is positive semi-definite. And the reason for that is that you don't want vectors to have negative, the square of this norm that I defined to be a negative number. And you also don't want to have zero norm unless you're talking about the zero vector. However, that is not enough if we want to play with spacetime, and we need to do geometry with spacetime. So in principle here, I'm not going to demand that the metric is positive semi-definite. We can also define a notion of angle now that we have it's kind of nice to have a notion of angle finally. Keep in mind that we didn't have, even though I drew things to illustrate, we did not have a notion of distance. We couldn't measure distances in meters. You can talk, how far are you from me? Well, I don't know, I don't have a distance. And the notion of angle didn't exist either, because there was no notion of an inner product that you could define. Now I can define a notion of angle between two vectors. For example, I define the cosine of the angle between two vectors v and w. By definition, this is going to be the ratio between GAB, the action of the metric tensor on the two vectors, right, divided by the norm of the square root of this thing for the two vectors. But let me write it like that.
Absolute value GAB, VA, VB, and the square root of the absolute value of GAB, WA, WB.
And that's a definition of a notion of angle. Coming from, it may remind you something like what you saw, that the inner product of two vectors is the modulus of the first, the modulus of the second, times the cosine of the angle between them. Well, this is the generalization of that notion to now a Riemannian manifold, or a pseudo-Riemannian manifold. This is of course defined as long as the vectors are not zero norm. So you need that the norm of V is different from 0 and the norm of W is different from 0, right? For non-zero norm vectors. You can also define a notion of orthogonality. So you say that V and
W are orthogonal if G, AB, VA, VB, or WB, sorry,
is equal to 0. And that's actually defined even if the norm of the vectors is 0. So it's kind of nice to have a metric. We have a notion of orthogonality, we have a notion of distance, we have a notion of angle. All right. What else can we do with a metric? Now that we have a metric, there are so many things. This is much richer. We can do so many things. Let's see. All right. A metric is degenerate at a point P in the manifold if we can find one vector in the tangent vector space to the manifold at that point that is orthogonal to every other vector. If you can find it, then we call the metric degenerate, at least one of them. Now, that happens if the matrix made out of the components of the metric evaluated at that point, it's singular in any basis. The matrix being non-singular, and therefore invertible, the matrix made out of the metric coefficients, if it's invertible, then the metric will be non-degenerate. And now, if the metric is non-degenerate, I can find a matrix inverse to this matrix, right? And I can find a twice contravariant tensor whose component in an arbitrary basis I'm going to write as G with superscripts, very similar to what we did in the second video, very similar to what we did in the special relativity video, but now a little bit more fleshed out. Now, this new twice contravariant tensor that is defined with indices upstairs, I'm going to define as the inverse matrix. The components of it are going to be, in any basis, are going to be the inverse matrix to the matrix made of coefficients of the components of the metric. So that is, in writing it in math, they satisfy, the two tensors satisfy that equation. That G, BC with upper indices is the matrix inverse, is the inverse to GEB. So if you multiply the two, you get the identity. Okay? The canonical delta, the identity. All right. Now, same as we saw in those other videos, the moment we introduce a metric that is non-degenerate, and therefore a metric inverse, a metric with the indices upstairs, then we can establish an isomorphism between two spaces that were completely different, like pears and potatoes. The tangent vector space to the manifold at a point, and the cotangent vector space to the manifold at a point, and if the metric is non-singular in the whole manifold, then we can do that at every point in the manifold. And that's nice. So from now on, we're gonna work, unless stated otherwise for some reason, we're gonna work under the assumption that the metric is non-degenerate in the whole manifold. Right. So look at that. That means that for every vector, these are the components of a vector, I can associate univocally a one form. And that one form is associated to the vector by means of the metric. In the same way, I can do the opposite thing here. I can associate to every one form, I can associate a vector using the metric inverse. Now you see, I call them V because the moment you establish an isomorphism between them, you basically can say, right, this one form, vis-a-vis, corresponds to the vector VB. So it's kind of the same thing, only the form version of it. In a similar way, what you do in quantum mechanics, you have a psi, a ket psi, and then you say, all right, I can do the bra version of that, and it's the same state, right? Even though this lives in a completely different space, now you have an isomorphism to say, no, it's this guy just made the bra version. The same way, this is this vector, but made the form version. And how do I do the form version? through the metric. Now, difference with special relativity is that in general, this metric will not be diagonal, as it was in special relativity. In the case of differential geometry, and of course it will be the case in general relativity, this metric here doesn't have to be diagonal. But you see, we can associate, and that's super important. In the past, remember, we couldn't have an inner product. The contraction between a vector and a one form, I insisted, is not an inner product because they live in different spaces. But now we have a way to associate something that lives in the tangent vector space with a representative of theirs that lives in the cotangent space. So we can associate, again, one-to-one elements of the tangent vector space with elements of the cotangent vector space. So much so that in physics, oftentimes we say this V represents a velocity. We say, oh yeah, this one form also represents that velocity, but the one form version. Keep in mind that these things not being diagonal or ones and their functions, they can be very different in a given basis. The way the components look can be very different, but they're associated one-to-one with each other. All right. Now, of course, we can do the same in general. This is what we call lowering and raising indices. The metric lowers and raises indices. You can do it with a tensor. Here's a twice contravariant tensor. I can lower the index C as I did. So the second index, I'm going to make it covariant. So now I related a tensor that was twice contravariant with a tensor that is once contravariant and once covariant. And I can do with the other index, right? And then you see how it is important to keep the relative position of the indices. That's why I insist so much on that when we do math about it. So a little detail. The same way that we say, VA and VA, you say, oh yeah, they represent the same physical object, right? In a way, this could be a velocity with index up, velocity with index down, whatever. In the same way, this isomorphism using the metric creates classes of objects that have associated ket, a vector, and a one form, right? That represent the same object. And you can say, I think, from this tensor, like this thing, oh yeah, it's representing the same thing as this one, only lowering and raising the indices. If this were, for example, I don't know, something like a stress energy density, having indices up or down, it's just different versions of the same thing. We can think of the same for the metric. So we can lower and raise the indices in the metric. Let's see, if I have GAB, imagine that I want to compute, so let me erase this. I want to compute the metric AB. So let me call this one C, right? GAB. So I want to raise only one. If I raise the two of them, I know what I get. I get the inverse metric. But what if I raise only one? What do I get? Well, we've done it already, but let's do it again. So if to raise the index C, I multiply by the metric. I want to make it a B. So that would be BC. But remember that the metric is symmetric. So I can write GBC, GCA. That's the same thing. And remember that this thing is the matrix product between the metric inverse and the metric. So this is the identity as we have here. So this would be the delta BA. So the metric with one index up and one index down is the identity. And that's true no matter. Remember that the components of the metric as a tensor field don't have to be constant. They could be functions. Every component of the metric can change with the point in the manifold. And also it doesn't have to be diagonal. And yet the metric with one index up or down, no matter where you are, is just 1, 1, 1, 1, 1, 1 in the diagonals. All right? Okay, that's cool to know. So the delta, these things are you represent as the metric. So AB, which is the metric, the components of the metric tensor, GAB, which are the contravariant version of the metric tensor if you want, so the inverse metric, and delta AB, they're all the metric, only with indices up or down. The metric tensor, I mean. I will abuse a lot, many times calling the metric tensor, although there's a such thing different between the two notions, right? But with a metric tensor, you define a metric. Well, so then I'm gonna just be calling the metric tensor many times, and hopefully bear with me, okay? That's what physicists we do all the time. So cool. Let's talk about the Riemannian versus pseudo-Riemannian and the metric signature now. Okay, we define the metric signature as the number of positive, negative, and zero eigenvalues with, of course, with his multiplicity of the real symmetric matrix GAB, which is made out of the coefficients of the metric. Now, in particular, in Riemannian manifolds, the signature, what we call Riemannian manifolds, the signature of the metric has to be non-negative. So, for example, you have plus, 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 right? However, we are deviating from Riemannian manifolds and we go to pseudo-Riemannian manifolds, and in particular to the choice that we call Lorentzian metrics. there are two possible conventions of that you can call Lorentzian metrics. You can have one positive eigenvalue and three or more negative ones. I'm just reducing to 4 eigenvalues because we're gonna work in general relativity with spacetime, so that's why I picked 4. But anyway, it could be any number at this point. But if it's one positive and the rest negative, this is the West Coast convention for a Lorentzian metric. And if it's one negative and the rest positive, is the East Coast convention for the Lorentzian, for tricking the Lorentzian metric. So with a Lorentzian signature, for the metric signature, these two conventions are totally equivalent. These two conventions are both correct as long as you keep consistency in their use. You cannot change from one to another, and you have to be really careful if you check books and you have some results that use one convention, some results that use the other, and you try to compare. This is bound to get you problems. Above all, if you do it for assignments, and then right away I can tell that you're using the wrong one, and that tells me that you don't really know how to do it probably, and that it's very likely that you were copying. So be really careful. Be really careful with that. Now, of course, as I was saying, both are correct choices, all right? You are free to pick whichever you want. I don't want to hear anybody talking anything bad about them, about any of them, all right? Okay, they're both, we have to love both of them equally. I'm gonna give them names just because West Coast, East Coast seems funny. I'm gonna call the West Coast convention, I'm gonna call it, just give it a name without meaning, right? I'm gonna call it the wrong convention. And the East Coast convention, I'm gonna call it the right convention. Again, both are correct. You can use whichever you want, but I hope that this is kind of self-explanatory, that I do prefer one over the other. I have my reasons. Anyway, this one is typically used in high energy physics, typically used by people who usually do not work with curved spacetimes. And this is typically used by people who work with relativity or quantum field theory in curved spacetimes. All right. So, if you want to discuss why I call this one the right convention or the wrong convention, which is purely my criterion, I mean, definitely I don't want anybody thinking that I can prove one is better than the other. But if you want to hear my arguments, one day I can tell you in one of the live sessions. Anyway, so we choose, of course, the right signature convention in this course. So we call our Lorentzian metric a metric with that signature. All right. Now, once we define a Lorentzian metric, we can we actually separate the vectors in the tangent vector space to the manifold at every point in 3 different groups. And the groups are these. A vector in TPM at a point P is time-like if its norm square is less than 0, is space-like if its norm square is larger than 0, and it's null if its norm is 0. This is kind of interesting because we can define, remember that the vectors in the tangent vector space generate curves in the manifold. This vector in the tangent vector space, it tells me what direction to walk in order to describe a curve in the manifold. So we can define a time-like curve as a curve whose tangent vector is time-like throughout the whole curve. And the same for space-like and null. All right. This defines the causal structure of the manifold. For example, at a point P in the manifold, right, point P, I have a point P prime. And we can ask, is this point P related causally related with P prime? Well, I have here all the curves that are time-like, and then is there one curve that is time-like that connects the two? If so, they're causally connected. One can be the cause of another. Now, a manifold is time-orientable if I can find time-like or null curves or non-space-like curves that connect all the points in the manifold with some other points in the manifold. If that's true, that means that there is at least one time-like vector field that is smooth, of course, and is time-like, and I can define it in the whole manifold. Having at least one time-like vector field that is defined and is smooth, of course, non-vanishing, and well-defined in the whole manifold, makes my manifold what I call time-orientable. There is a notion of time that I can, if this were space-time, there would be a notion of time. So this is math and not physics yet, but still the notion of time orientability is related with the fact, okay, you can find at least a time-like, something with negative norm vector field that is non-vanishing and covers the whole manifold. So we can extend a notion of time, in a way, a notion of future, a notion of past in my manifold. I can classify things in terms of being at a point. I can classify, going through those curves, what is in the future, and going back through those curves, what is in the past, okay? It's a notion of time. All right. any non-compact manifold, so you can think of it as manifold without boundaries, right? You can always associate a Lorentzian metric to it. You can always get a Lorentzian metric. But there are some non-compact manifolds that you can't give them a Lorentzian metric. Like, for example, a sphere. You cannot give a Lorentzian metric to a sphere. Now, for manifolds that are Lorentzian, the typical convention is that both, well, this coordinate basis I wrote here doesn't have to be, of course. This is also true in an arbitrary basis, of course. I could have written AB, AB. Huh? Now, it's typical that the indices run from 0 to n minus 1. Okay, as we did in special relativity. And because of the symmetry of the metric here, separating the 0 from the rest, typically we call the 0 is the different one, you see. We call the 0 the time component. Well, we have defined, on the one hand, affine connections and covariant derivatives, and on the other hand, we have defined a metric. So in a Riemannian or pseudo-Riemannian manifold, a connection and a metric can coexist, and they have nothing to do with each other in general. But there is only one particular choice of connection that is what we call compatible with the metric. That is what we call the Levi-Civita connection. The Levi-Civita connection is the only symmetric connection. Remember, the only symmetric torsion-free connection is the same thing, such that the covariant derivative of the metric is 0. That is the condition that we call compatibility with the metric. Why do we want that? Well, we want that is special, because if we give the metric value to actually tell me about distances and inner products and relationship of vectors with each other, angles and so on, I want that the variation of the metric, I want the metric to be parallel transported around the whole manifold. I don't want the metric to start having variation when I vary through the whole manifold. I want the metric to really capture the structure of the angles between the vectors. And if the angle of tangent vectors to geodesics change because they're curvature and things like that, I want the change not to be because the metric changes. I want it to be because there is curvature associated with it that is not related with changes in the metric. Right, so I really truly want the metric to have 0 covariant derivative. So I want to choose a particular notion of covariant derivatives, a particular affine connection that satisfies this. This is the one that's going to have physical meaning when we talk about relativity. Remember that we fully characterize covariant derivative by characterizing the coefficients of the connection. So what are the coefficients of the connection that satisfy this condition? Well, let's see. This condition in coordinates implies that nabla A, G, B, C has to be equal to 0. But we also know how to take the covariant derivative of a tensor that is twice covariant, above all in a coordinate basis, right? We know in a general basis, but let's do it in a coordinate basis. If you remember, in a coordinate basis, we have that the covariant derivative, let's say mu G nu sigma,
it's equal to the partial derivative mu G nu sigma, and now we have to subtract because it's covariant, remember, the connection, and then we contract. First, the upper one, let's call it, what do we call it? Let's call it rho, maybe. Rho. And then we contract the rho, and we have here G nu rho minus gamma rho, and then mu and the other index, which is nu, and then this is G rho sigma. Right, that's the covariant derivative of the metric tensor.
But we know that the metric lowers and raises indices, so we can abbreviate, we can call this guy gamma, and we lower the rho index to nu mu sigma, and we can call this guy, again lowering the index rho now to sigma, gamma sigma mu nu. Alright? So if we write that, and then we know that this thing is equal to 0 to find for the particular, for the Levi-Civita connection, we know that this has to be exactly equal to 0, so we get the relationship that partial mu G nu sigma it's equal to gamma nu mu sigma plus gamma sigma mu nu. Now, this equation actually allows me to fully determine the coefficients of the connection in terms of derivatives of the metric and the metric itself. Shall we do it? Shall we prove it? Can you see it? This is another of those things that I call easy exercise. It could be a small part in a final or a midterm or something like that. Let's prove it. Let's do it. What we do for that is that we write this equation 3 times. Let me write it one time. Let me just first time.
Partial mu G nu sigma is equal to gamma. Let me write the sigma one first. Sigma mu nu plus gamma nu mu sigma. It's the 2 terms, I just wrote it down the other. Okay. Just to align them. I want to align them every way.
Now I'm going to do a swap here of mu is going to swap with nu. And then I'm going to write the result here. So if I swap mu and nu, I get partial nu G mu sigma, I leave it as is, equals gamma sigma, now nu mu, plus gamma mu nu sigma. Then I'm going to write a third variation by doing another change. Here the change I'm going to do is mu is going to go to sigma, nu is going to go to mu, and finally sigma is going to go to nu. Doing those changes, I'm going to get the following equation. So let's see, mu to sigma, so partial sigma, nu to mu, so this is g mu, sigma to nu, it's equal to, now the same here, sigma to nu, so this is nu, mu to sigma, right, and nu to mu, plus, here the same thing, nu to mu to sigma, and sigma to nu. So I'm gonna put a minus sign here, okay? And I'm gonna sum them. So let's see what we have here. I have gamma mu sigma nu, gamma mu nu sigma. But this connection is symmetric. So it's symmetric in the two last indices, right? So this thing is exactly the same as this one, but with the opposite sign, so this thing cancels. Wonderful. How about this one? This one, nu sigma mu. Nu, mu sigma, this one cancels with this one because again the connection is symmetric, so the two last indices, the coefficients of the connection are the same. They're symmetric under the change of the two last indices. Alright, so what am I left with? I'm left with the following. Let me just write it. So I have partial mu g nu sigma
plus partial nu g mu sigma minus partial sigma g mu nu, okay? That is equal to.
So we have here gamma sigma mu nu, but also gamma sigma nu mu. These two things are the same because again the symmetry of the coefficients of the connection in the second and third indices. So this is twice gamma sigma mu nu.
This gamma sigma mu nu as partial 1/2 of partial mu g mu sigma plus partial nu g mu sigma, right, minus partial sigma g mu nu.
Well, now to get back the coefficients of the connection in the way we defined it with the first index being upstairs, we can now multiply by an inverse of the metric here. So if we multiply both sides by, so if I have this thing, sigma mu nu, we remember that we can raise this thing by multiplying by g rho sigma, right? If we do that, this thing is exactly equal to gamma rho mu nu. Okay, so we multiply by g rho sigma both sides of the equality, and we get on the left gamma rho mu nu equals to 1/2 and then g rho sigma of partial mu g nu sigma plus partial nu g mu sigma minus partial sigma g mu nu. And these are the coefficients of the connection uniquely determined through the metric and its derivatives. So proof, this is the proof that there's only one connection, there's only one connection such that this is true, and the one that satisfies the equation, there is only one. Before we continue, I need to tell you something. The coefficients of the Levi-Civita connection, remember the connection that's symmetric and compatible with the metric, are called the Christoffel symbols. And maybe some of you have been reading GR somewhere, have heard about the name Christoffel symbols. So maybe you were tempted to call in general the gamma, A, B, C Christoffel symbols from the beginning. Don't do it. Call them Christoffel symbols now that we have a connection that is compatible with the metric. All right, let's go back to the main video. Another exercise that I could ask, for example, that I'm going to prove here is show that the Levi-Civita connection defines a covariant derivative such that the parallel transport of vector fields preserves the norm and the angle between vectors. And that actually means that it preserves the nature of time-like, space-like, and no. A vector field, when it's parallel transported, if it's time-like, will be time-like throughout the whole parallel transport. If you remember, now the Riemann tensor was a function of the coefficients of the connection as we found in the previous video. Now we can substitute the coefficients of the connection in the definition of the Riemann tensor to have an expression for the Riemann tensor for the Levi-Civita connection. And then we can talk about what are the symmetries of that. Now, if we do that, we are restricted to a particular connection, and that particular connection, if it's, the Levi-Civita connection, it will induce more symmetries even in the Riemann tensor. That is another super easy exercise. It's a grinding exercise in a way. Just substitute the coefficients of the connection by the coefficients that we found and check that these properties are satisfied now. Some of them already were satisfied for any connection. Some of them were satisfied for any connection that was symmetric. But these are satisfied for the Levi-Civita connection. So some of the old ones plus a new one. In particular, there's this new one. Now, you have symmetry, anti-symmetry also on the last two indices. And that implies, together with the others, that you get also symmetry with respect to the exchange of the pairs of indices, like CD by AB is symmetric. Notice that this Riemann tensor has all the indices downstairs, all the indices being covariant. And that's fine, because now I have a metric, and you know that we can raise and lower indices with the metric. So if somebody asks, then what is this thing? R, A, B, C, D. Well, this is nothing but G, let's say, I don't know, E, D of R, A, B, C, E. All right, so we know how to lower and raise indices, therefore being upstairs or downstairs is not a concern. These symmetries actually imply also symmetries on the Ricci tensor. In particular, the Ricci tensor will be symmetric. So if the Ricci tensor associated with the Levi-Civita connection is symmetric. Now, there are some interesting tensors, of course, that we can define and have information. Remember, R has information about curvature, remember that R tells you how things, when they move in the manifold, in geodesic trajectories in the manifold, how they deform, how the different geodesics get attracted to each other or separated from each other. Okay, and this is important. Let's see something really, really curious from differential geometry that has deep implications in physics. Let's define some tensors that are relevant, and let's talk a little bit about them. All right, so there's these interesting tensors that I defined here. Let me talk about them. We have the Ricci tensor. The Ricci tensor is the trace, as you can tell, of the Riemann tensor in the second and fourth indices. Then we have the Ricci scalar, which is the trace of the Ricci tensor. And then we define the Weyl tensor. This Weyl tensor looks very involved for a definition. You're going to have a full assignment exercise on the Weyl tensor where you're going to practice and understand a little better the Weyl tensor and derive things. So I'm not going to include the derivation and where this comes from and what it means, but you can tell it can be thought of as the traceless version. So this thing, the Weyl tensor, happens to be traceless. The Weyl tensor satisfies that C, A, B, C, B, this thing is 0. So it's basically kind of, if the Ricci tensor is the trace of the Riemann tensor, the Weyl tensor is the traceless part of the Riemann tensor. Now, they're particularly useful because the Ricci tensor actually inform us, like if you have in mind you have a box, right? And that box moves following geodesics. If you were thinking general relativity or something like that, there's a box of free falling points. Like you have a lot of free falling points. And what happens with them as they move through in space-time? Well, gravity is going to do things with it. So curvature of the manifold is going to deform the box. And it's going to change the volume of the box and also deform the shape of the box. So there's going to be shear and there's going to be change of the volume. If you think gravity, I don't know, I would love to have the classroom in front of me to ask, what do you think in gravity you can associate with change of shape? Which change like in a way the constraining the box, like, you know, we like stretching the box. The Weyl tensor is responsible for stretching the box, keeping the volume constant. What do you know about gravity that does that? Tidal forces. And indeed, the Weyl tensor is strangely linked with tidal forces. You will have a full exercise about tidal forces as well when we see GR. Now, let's just see tidal forces, you see? Because I think those things never get old. So if you have, say, tidal forces come, in mind that this is a source of gravity, like the sun or something like that. And you have here the moon, whatever. And you have here the earth, right? And you have, say that you have an atmosphere and water, say the earth is solid, whatever. So tidal forces, this is without deforming, right? Tidal forces, this would be like that without forces, right? Let's see. Mind that this is the body of water surrounding the planet. Tidal forces come because of the difference in gravity that you have at the extreme of the planet as compared to the other extreme of the planet, right? So that difference in forces stretches the planet in both directions. It's a difference. You have a force here that is stronger because it's closer to the center of gravity than the force here. That generates a differential of force, right? That's stretching. This is exactly what you do when you stretch, a difference of force between the two extremes. So with a planet in there, tidal forces are going to be like that, right? You're going to be doing that with water. Like, I mean, maybe that's an exaggeration. But basically it takes the planet and stretches like that, actually preserving the volume. So these things get, I didn't draw it like that, but stretches it doesn't make more water. Stretches the water like this, if you want. Now, this is important in popular science too. When you see it, now you battle it. Please, you battle it, because oftentimes when people who don't know science do the animations for science, they screw up. I remember a video by Neil deGrasse Tyson where he was talking about how the moon and the sun create tides, and how tides create two bulges. Exactly what I'm saying here. So it makes the thing here and yeah, like that, two bulges on the two extremes, right? I mean, symmetric bulges, right? And the illustrator, in the meantime, while Neil deGrasse Tyson was talking, had no other best idea than have the moon and the sun on both sides of Earth, the moon creating one bulge and the sun creating the other, and that is ridiculous. Of course, people ask, oh, that something's fishy, because the sun and the moon are not always opposite, and but of course they're not. I mean, because it's stupid. Just one body already creates two bulges because you're stretching the freaking planet. All right. Sorry, I had to say it, Pete. Like these things get to my nerves when people misinterpret the science and don't care to actually clarify. So you're there. It's your responsibility to actually, when you see things like that, correct them. Okay. So yeah, again, tidal forces are difference, if you want, of like basically the difference in force stretches the planet. Okay. There's a stronger force here, a smaller force here. So the net force is stretching. And keeping the volume constant. That's what you do. So you feel a force like this, right, in this direction and this direction. Is when you stretch something, conserving the volume. Get a plastic ball or whatever and stretch it like that, conserving the volume. So now that we understand a little bit more tidal forces, perhaps, I can tell you that the biotensor is going to be the responsible for those deformations that preserve the volume but change the shape. And the Ricci scalar is the one that when you write the geodesic deviation, the terms that actually change the volume. Okay, like being for example, the geodesics converge and then the volume is smaller, but also gets stretched and then the shape changes, so both happen at the same time. Now, let's count. Oh, by the way, the bitensor has the same number of symmetries as the Riemann. In fact, they have the same symmetries, right? It's literally kind of the traceless version of the Riemann. So all the symmetries that it has, are inherited by the bitensor. But you will revisit the biotensor in an exercise. For now, let's do what I consider a very interesting observation of differential geometry that has impacts in physics. Let's count the degrees of freedom of the Riemann tensor, the Ricci tensor, and the biotensor, shall we? With all these symmetries, when you have symmetries in a tensor, that reduces the number of independent components. For example, the symmetric matrix has n times n plus 1 divided by 2 independent entries, and antisymmetric one is n times n minus 1 divided by 2, and so on and so forth, and not the full n squared that you would have without symmetries. Now, we can write at a table here using these symmetries, and again, I'm not going to tell much about it because there's an exercise about all that, but let's write at a table the number of algebraically independent components of, I'm going to have here,
the Riemann tensor and the Ricci tensor. Right? This is the number of independent components depending on the dimension of the manifold. So I'm going to go dimension 1, dimension 2, dimension 3, dimension 4.
And let's start with dimension 1. Dimension 1 is trivial. There's no notion of curvature. You can prove that to satisfy all these symmetries, the only possibility is that the Riemann, all the entries are 0 exactly. So 0 degrees of freedom, 0 algebraically independent components for both the Riemann and the Ricci. All right. Now, what happens in 2 dimensions? Well, in 2 dimensions, you can have curvature. There's only one component that is independent in the Riemann and also in the Ricci. And actually, everything can be characterized in 2 dimensions by the Ricci scalar. The Ricci scalar is characterized in the full freedom that you have in curvature. So that makes sense, right? I mean, in 2 dimensions, imagine a surface of 2 dimensions could be sphere kind of curvature or hyperbolic kind of curvature at every point, and then combinations of them as you move, but that's only fully characterized by a scalar. Okay, what happens in 3 dimensions? Well, in 3 dimensions start to be less boring gravity because in 3 dimensions you would have 6 degrees of freedom for the Riemann tensor. So things can be, the geodesics, when they go and follow the curve trajectories that in the curve manifold, they can have more freedom to do things. But notice that still the Riemann is fully determined by the Ricci. There's the same number of degrees of freedom in the Ricci and the Riemann. If I know the Ricci, I know the Riemann. The biotensor in this case contains no information. All the information is in the Ricci. It's in the trace of the Riemann tensor, nothing on the traceless part. What happens in 4 dimensions? Aha! In 4 dimensions, the Riemann has more information than the Ricci has. So not all the information about how the geodesics curve when they follow the the flow, the geodesic flow in the manifold, is not all contained in the trace of the Riemann tensor. There is information contained also in the traceless part, in the Weyl tensor. That's super interesting because the Weyl tensor is the one that's responsible for the deformation of the shape preserving volume, which is the responsible for if the curvature of the manifold represents gravity, that's the responsible for tidal forces. So for space-time dimensions, for a space-time manifold, is the smallest number of dimensions where you can have non-trivial tidal forces, where you can have what I call non-boring gravity, gravity with the richness that we have and the importance that we have, and tidal forces being so important for the universe as we know it. So it's kind of interesting, right? You need at least 4 space-time dimensions, well, 4 dimensions in your space-time manifold in order to have something like tidal forces. So I think that's a cool point to consider. All right, let's see one more notion before finishing this video. Let's talk a little bit about conformal transformations. A conformal transformation is a transformation that scales the metric with a factor that may depend on the point. So let me just clarify here that this can depend, of course, on the point of the manifold that you are. So this would be GAB. Okay? So it's a scale square. It's a scale factor that scales the metric depending with a different value depending on the point where you're looking. Conformal transformations, you can quickly prove they preserve the angles between vectors. How do I know? Well, let's check it. So if you have the angle between two vectors, remember the cosine of alpha was defined as
we have here the GAB, VAWB, and then divided by the square root of GAB, VA, VB, and then the square root of JAB, WA, WB.
If we do a conformal transformation, this becomes, so let me just write under a conformal transformation omega.
This becomes omega squared GAB, VA, WB, and then we have here the square root of omega squared GAB, VA, VB, and then we put everything here, omega squared GAB, WA, WB.
And of course this cancels that. So the angle is the same. However, they don't preserve the norm of the vectors. Now, preserving the angle means that they preserve the causal structure. So if a curve is time-like with a particular metric, if I conformally transform the metric, the curve will still be time-like. Because the angles, that is what tells me if something is time-like or space-like or no, the angles don't change. Conformal transformations don't change the angle between vectors. Conformal transformations change the normal. Another interesting factor here is that the Weyl tensor is conformally invariant. By that I mean, if I make a conformal transformation, one can prove, and is another practice exercise that is just grind this, substitute the coefficients and you'll see it. The Weyl tensor is invariant under conformal transformations. That's kind of cool, because that means that if I actually give you the Weyl tensor, I'm univocally defining the causal structure. And that's particularly interesting because remember that two different metrics give the same causal structure, the same relation between time-like, space-like, and no, if and only if they are related by a conformal factor. So if the Weyl tensor doesn't change and the conformal factors, they will have the same Weyl tensor. So the Weyl tensor is what defines, is what establishes, what fixes the causal structure. Look how important that Weyl tensor is. That's why it will have a full exercise for itself in an assignment. All right, conceptually really important. That also means that there are families of spacetimes that have the same causal structure, and those are related by conformal factors. So to determine, giving me the causal structure of a spacetime, so at every point what does it mean to be time-like, space-like, or no, doesn't fully determine the metric, but determines a lot. Determines the metric except for perhaps a conformal factor. And we will see, when we talk about general relativity, what actually determines that conformal factor. There's one more tensor that I already erased, but we didn't talk about, the Einstein tensor. Let's talk a tiny bit about it. Well, the Einstein tensor, of course, makes more sense when we talk about general relativity, but as an object in differential geometry, it's still interesting. It can be proven, and in fact, this was something that I may want you to do for practice, because this was actually an assignment exercise, the first year that I taught relativity, using Bianchi's identity, prove that the Einstein tensor is divergenceless. Like that. This is a symmetric tensor, by the way, and prove that the divergence of the Einstein tensor is 0. That's one of the most important properties that this tensor has. Hint to do it, you prove it from the Bianchi identity. The Bianchi identity allows you to determine two things. to determine the divergencelessness of the Einstein tensor and also the value of the divergence of the Weyl tensor. But I'm not going to get too much into that. I just wanted to introduce the tensor here as an interesting one. It's interesting above all because it would give you at the level of differential geometry a good practice exercise, which is prove this using Bianchi identity. All right, as the last thing that we're going to see on this video, we're going to go and revisit that notion in popular culture that perhaps geodesics are those curves that minimize the length between 2 points, right? I'm pretty sure you have heard that. How true is that and what that actually means is we're going to be seeing more rigorously right now. All right, imagine that I have 2 points in a manifold and I join them with a curve, gamma of s. So I have 2 points and a curve that is either space-like or time-like, okay? So if it's space-like, if the points are space-like separated, they would be space-like curves. Then if it's space-like, you read space-like and length here. And if it's time-like, read time-like and time, okay? Because we're going to define the notion of proper time and proper length of a curve simultaneously. Okay, so I have this curve gamma s that is joining the points gamma 0, gamma 1. So I have here gamma 0, gamma of 0, here gamma of 1, right? And I have this curve like right there. And then I say, okay, the coordinates of the curve, when I map it to, I have a coordinate basis to map it to Rn, the coordinates are x mu s, and the tangent vector v has coordinates derivative of x mu with respect to s, of course. I write a circle here instead of a dot because this parameter is arbitrary. So just to, this parameter is nothing special, it's some parameter that parameterizes the curve between the point gamma of 0 and gamma of 1. So I will use usually dots when I'm talking about a particular parameter. Anyway, so we define the proper length between the 2 points gamma 0 of gamma 1, the proper length of the curve, the proper length of the curve between the points gamma 0 and gamma 1 as the integral from 0 to 1, integral on all the parameter, integral where all the value variation of the parameter from 0 to 1 of the norm of the tangent vector. And that makes sense as a length, right? Because what I'm doing, the tangent vector is the velocity. And the velocity tells me how much length I cover per step that I take. That's the velocity. So this s is kind of the step, the time in a way, and the velocity is how much length I cover in a way, in an infinitesimal step, right? The velocity tells me basically how big is the step that I'm taking when I move in the direction of the curve, right? So the norm, integrating the norm of the tangent vector, integrating the norm of the velocity, does give you, along the trajectory, does give you a length, all right? So this is definitely the notion of length. And of course, the norm of the velocity vector now exists because we have a metric space, a Lorentzian manifold that we have here, right? We couldn't do this before because we didn't have a metric, but now we do. All right, so we write this in terms of the coordinates of the tangent vector and the metric tensor, and then this defines the length of the curve, all right? Very nice. Now we can ask, what is the condition that a curve has to satisfy to extremalize this length? So a minimum, a maximum, or a saddle point, right, of this length, of this proper length, or proper time, if it is time-like. This is a problem, an Euler-Lagrange equation, a Hamilton's principle problem, right? Because I'm telling you that you can treat this as an action, because it's basically extremalize L, so variations of L equals 0, for fixed initial and final point. This is literally the problem of finding the Euler-Lagrange equations. And if you find them, and don't worry, because we will do this exercise in the general relativity block to find the geodesic equation through a variational principle. So I'm not going to do it in detail now because the video is already long. But it's kind of remarkable that you get a covariant derivative. When you take, you remember how to do it? You take this is a Lagrangian, so you need to take derivatives of the Lagrangian with respect to the velocities and so on and so forth. And you get a covariant derivative? Yes, you do. You're gonna get Christoffel symbols. All right. And don't worry, we will see how. But you can do it as it's a good exercise to do if you want. Now, the equation, the Euler-Lagrange equation that you get is this one. Does it sound familiar though? What is this equation telling me? This equation tells me that the directional derivative in the direction of the tangent vector of the curve, so the directional derivative in the direction of the curve, of the tangent vector of the curve is proportional to itself, with some proportionality factor. That is actually the time variation, the derivative with respect to the parameter of the norm of the velocity of the same vector, the tangent vector. Remember, these are the coordinates of this vector. Do you remember what we call the curves that satisfy that the directional derivative of the velocity in the direction of the curve is proportional to itself? Those were the geodesic curves. And indeed, the geodesic curves remember, the velocity doesn't change direction. They go along the curve. Always, as they move along the curve, the velocity always points in the direction of the curve. They may change velocity. They may change the magnitude of the velocity. They accelerate and brake. But that's precisely this, right? This ds of the log v is non-zero when the velocity changes. You are going through the curve at different speeds. But this is a geodesic curve, and that means that I can find an affine parametrization. I can find a parameter, a different parameter, tau maybe, for which the curve becomes a geodesic. And if it's a geodesic, the variation along the curve, as I move along the curve of the tangent vector, is zero. And that means that the norm of the tangent vector cannot change. And because it cannot change, this term will be zero. So in the case of this is a geodesic curve, this is the equation for a geodesic curve, as we saw it, and that means that with affine parametrization, it becomes, and let me just call it a dot because it's going to be now a derivative with respect to the affine parameter, mu and a nu here, and a nu here, equals 0, which is the geodesic equation. So indeed, the curves that extremalize proper length and proper time are the geodesics. So that notion of popular culture has something of truth there. But even so, there's something interesting about it, because sure, for space-like curves, yeah, it looks like it's reasonable to expect that it's going to minimize the proper length between 2 points, and those are the geodesics. The geodesics minimize proper length. But is that true for time? Let me put it in a different way. Geodesic trajectories. Are geodesic trajectories those that minimize or maximize the proper time between two events? And the answer is non-trivial. In fact, geodesic trajectories maximize proper time. I can give you a very quick argument that shows that proper time will be actually maximized in a geodesic. So think of flat spacetime, x, ct, and I give you 2 points, the origin and this one. What is the geodesic between those two? What is the inertial trajectory between those two? Well, just this straight line like this. You just go in time, you just sit there and arrive to the other event, and that is the geodesic. That's what would happen in absence of forces. Is that maximizing or minimizing the distance? Then you may say, sure, it's minimizing, right? Because I can always think of a way to go like this, and this is more distance. Not quite, because we are in a Lorentzian manifold. What is the norm of the tangent vector that goes like this and the tangent vector that goes like that? Let me just make it bigger. What is the norm? If I go like this with this velocity, what is the norm? This is a null vector. The components of the vector is one space-like, one time-like. The norm of that vector is 0. So you can get trajectories really, really close between 2 points to the light cone, like this. I go like really, really close to the light cone, like that, and the norm of those vectors is going to be tiny as compared with the norm of these vectors, because the vectors that are time-like have no spatial component that would subtract from the norm when you compute the norm. So indeed, and this is very important, geodesics actually maximize proper time. Time-like geodesics, that are those that can be traveled by people, by observers, maximize proper time. So this is kind of cool. Because you can solve a problem without doing any calculations. I ask this problem often. I get 2 clocks. I mean, it's a problem that actually Feynman asked. I think Feynman, it's attributed to Feynman. So imagine that I have 2 clocks, one on each hand, and they're synchronized. And I throw one up and catch it. And then I ask you, which one experienced more time? So the 2 clocks, one of them would be delayed with respect to the other, because experience more time. One of them, like if one is showing 12 o'clock, the other one would be 12 o'clock plus something. Now the question is, which one experienced a longer time? And then when I ask this, students usually go on crazy avenues. They go and compute, oh, but the velocity is this, and but then acceleration of gravity. And the answer is very simple. These are non-geodesic because they're not free falling. I'm holding them. I'm preventing them from free falling. This one was free falling for a while. When I throw it up and fell down. So this one experienced some geodesic motion. Geodesic motion maximizes proper time. So this one, the one that was thrown, maximized the proper time, experienced the longest time. All right? So you see, you can answer it like that without calculations. All right, this is all I wanted to talk to you about in this video. It's been a lot in this video. In the next one, we're going to talk about isometries and killing vectors. And also, we will do a couple of differential geometry exercises that are interesting, that are also a good reference, I think, for you. Until I see you then, take care.